As Patrick said, I work for the Met Office Hadfield Centre, so that's the climate research part of the Met Office. And today I'm going to look at sort of slightly longer range predictions than we were talking about so far today, really. Well, back to the first talk, actually, talking about seasonal forecasting. And also improved estimates of sort of what is the baseline risk that we are currently exposed to in the current climate. And so I'm going to try ambitiously to do these two things at once, which I've been advised not to do. Right, so here looking at extreme seasonal climate variability, I think the point I'd like to make is that there have been, in recent times, a number of seasons that have been characterized by a particular weather type. So, for example, in winter 2013-14 here, as we saw in Matt's talk just now, a very, very wet winter for the south and southeast of the UK. This is a picture of the Thames. And that lasted pretty much for most of the winter season. And in the same way, for a cold winter, 2009-10 here, example of Heathrow covered in snow, that also lasted for most of the winter. Wet summers, so the famous picture of Tewkesbury we saw a second ago too, from 2007, very wet weather for almost the whole summer for the UK. And then hot summers, this is back a little bit before my time, but just. But this is the hot, dry summer of 1976, which some of you will remember well. So we'll go back to that one in a minute. So these seasons are basically characterized by a particular set of weather conditions, which of course we'd like to predict. So thinking about risk, so if you want to look at risk this coming season, then obviously a seasonal forecast is a good place to look. So that's dependent very much on the current state of the global climate variability, so global modes such as the El Niño Southern Oscillation in the Pacific, for example. And so that will modify the baseline risk for that season coming. Whereas the baseline risk, so beyond the range of predictability in most senses, for the next decade, what can we expect to see for extreme seasons in the current climate? And that's going to include unprecedented events that we haven't seen yet. So it'd be really useful if we could try and define what our true exposure is to the natural, internal variability of the climate system. And then this last one here is the climate change modified risk, which is a mid-century sort of how the risk will change in a warming world. And that's sort of traditionally what the Met Office Hadfield Centre has been looking at. And I'm not going to talk about that today. I'm going to focus on very much these two here. So I'm going to give examples of our seasonal forecasts and some improvements we've had recently in the skill over winter and summer. And then I'm going to switch to looking at this idea of the baseline risk. It's something we call the on-scene method, which tries to identify extreme events. And we do this using the same set of ensembles that we use for the seasonal forecasting. So this is very much sort of two sides of the same coin, if you like. So we'll come back to that. So this is just sort of showing what sort of timescale we're looking at. So Matt's talk just now was really talking about the sort of the days to a week. I'm really looking at the months to seasons. And then the climate slide we're not going to talk about today. So if I just think about a recipe for seasonal forecasting, I thought I should try and very quickly explain what a seasonal forecast is. So this is really the ingredients you need. You need a global climate model, you need a very large supercomputer, you need observations of the climate state to initialize that model with, and then you need to run a hindcast, a retrospective forecast, so assessing your performance in the past as if you only have the information you have before each of those years. To assess the skill, there's no point issuing a forecast if you don't know it's skillful, and to correct some biases. Before it's involved in a discrete grid, you have an atmospheric component, an ocean component, a land surface, a sea ice, etc. So this is very much the core of our climate model. That is called HadGem 3 GC2 in our case. So this is the same model that, a very similar version that's been used for the IPCC upcoming AR6. So in the atmosphere, we're looking at sort of a 60-kilometre model globally, coupled to a land surface, and then in the ocean, we're looking at 1/4 of a degree, coupled to a sea ice model. So this is quite high resolution in terms of a climate one, for example, quite low resolution, of course, compared to a 5-day weather forecast. But it's an important thing is this is coupled. So unlike your weather forecast, still true today that very much is an atmospheric weather forecast. This is a coupled system, so you can have more developing variability through the ocean as well. So we run very large ensembles. Now, for very large ensembles, slides order's changed. Okay, just going to very quickly show the benefit of increased resolution. This is a movie I've shown for a few years now. I should probably replace it, but this is the 1/4 of a degree ocean resolution compared to our old 1 degree ocean resolution. All I'm showing here is sort of 2 years of monthly temperature at 370 meters depth in the ocean. Just really show the extra detail you have on the 1/4 of a degree. So we see all these eddies, for example. These are the Guinness rings shedding off South Africa. This is this cool Gulf of Mexico loop current being shed into the Gulf of Mexico here. These features don't really feature here. But more importantly, perhaps, we have these much sharper gradients of temperature for the Gulf Stream here, much sharper transition than we have this blurry picture here. So perhaps a potential for more ocean-atmosphere interactions. So we need a nice large supercomputer, and thankfully Met Office has got one. Major UK government investment of almost 100 million. It's housed in a new building across the road, across the M5 from the Met Office in Exeter. So basically this means we can run far more high-resolution simulations. Computers aren't very exciting. They try to sort of jazz it up by using some sort of blue lighting here, but essentially it's just a lot of boxes. But that's a very, very useful piece of kit for us to use. What do we need to do then to initialize our model? So we want to start our model from the current state of the climate system. So you need to know things like what the ocean's doing, what the heat content's doing, what the dynamics are doing, what ENSO is doing, what the state of the sea ice is. It'd be nice to initialize land surface as well as some sort of external boundary conditions. What stage of the solar cycle are we at? What's our anthropogenic greenhouse gases, our aerosols? Are there any volcanoes that have just gone off that we need to factor into our forecasts? So we try and incorporate all of this, and we try to initialize or use as boundary conditions all this information to make our seasonal forecasts. Just one example. So how do we get the ocean data? I quite like this one. So in the last sort of 10 years or so, we've had these Argo floats. This is sort of 3,000 autonomous floats that just sort of do a random walk throughout the world's oceans. This is a snapshot here. These dive down to 2,000 meters depth and give us temperature and salinity profiles every 10 days or so. So a real step change in our ability to observe the subsurface ocean. So very, very quickly, that's a whistle-stop tour. So we've got our climate model, we've got our supercomputer, we've got our observations. What we want to do now is to run some retrospective forecasts to see how well we can actually forecast things. So what would we like to be able to predict? Well, for winter, in terms of predicting risk over Europe for winter, we'd like to be able to predict the North Atlantic Oscillation. That's the NAO. Now, the NAO is sort of the prime mode of atmospheric variability in the North Atlantic sector. It's basically characterized by a low pressure over Iceland, a high pressure over the Azores. We have a positive phase, then we have a deeper low and a higher high, so a stronger pressure gradient. In geostrophic balance of that, we have stronger storm track. We end up having milder and wetter conditions into northern Europe. Whereas in negative phase, we have anomalously weak pressure over Iceland and the Azores, a lower pressure gradient, a weaker storm track. It meanders more. We end up with more of a continental influence for our weather. So we have cold and dry conditions typically, snowy conditions even over northern Europe. That's talking about snow. These are the two satellite pictures of winter 2009-10 and 10-11, when the whole UK was pretty much covered in snow. So this is something we'd like to predict. These are just examples of famous winters. 62-63, we had a negative NAO, very, very cold winter over the UK and Northern Europe. 2009-10, a very similar pressure pattern, very similar results. 2011-12, the opposite. So we have a positive NAO, so a really active storm track. We have very warm and stormy weather into the Northern Europe. So we'd like to predict this. And the challenge really is that this was thought to be basically a chaotic mode of variability in the atmosphere until just a few years ago. But sort of over the last sort of 10, 20 years, research has been done to try and identify what some of the drivers are for North Atlantic Oscillation. For example, what happens in the tropical Pacific, sea surface temperatures in the North Atlantic, the sun, sea ice, volcanoes, the QBO, quasi-biennial oscillation, the Mansion Junior Oscillation. So all of these things are known or thought to impact the NAO. And basically, we've been trying to improve our models to be able to incorporate this variability in our climate models and the tenor connection correct to the NAO. So that's been quite a success. We put it together with our high-resolution model, and we have the ability to predict the winter NAO with a skill score of about 0.62 in terms of a correlation, which is pretty high. It's sort of getting to a stage which is useful for making seasonal sort of climate services. So this is predicting the winter NAO for DJF, December, January, February, from the 1st of November. So it's 1 month lead time forecast. And so you can see some very prominent winters. So here's 2009-10, the very, very cold, snowy winter we had. The black is the observations. The red is the ensemble mean prediction for the model. You can see that we pick out that cold winter. We pick out the 11-12 and the evolution. So although not perfect, it's a pretty good forecast for the winter NAO now. So we use a large ensemble. So here I'm just showing the ensemble mean, but we've used 40 members here in this forecast. So we have potential to give warning to decision makers. Now, this result sort of first came out in sort of 2014, so that's about 4 years ago now, and we've had a chance to start exploring some of those climate services, which we've gone here. So lots of things are correlated with the winter NAO. So we have UK electricity demand, for example, that's anti-correlated. The sign's been flipped here just for convenience, but you can see that follows quite nicely the NAO. So in terms of really cold conditions, you also need higher demand for electricity. Winter airport disruptions at Heathrow is a quite strong correlation with the amount of delays to Heathrow operations and the seasonal NAO forecast. Slightly more obscure one perhaps, but shipping in the Baltic Sea, very related to sea ice cover, that's related to the NAO. Or winter river forecasting. So we have a lot of, I think it was mentioned earlier, we have a lot of skill from persistence due to the geology on the east coast of the UK, but the NAO gives us skill on the west coast due to the westerly storm track, and you combine these two together, you can have some quite nice forecasts for winter river flows. So these are all sort of growing examples of climate service prototypes that can help us to identify the risk of an extreme season for particular sectors. I'd like to very briefly mention European summer rainfall. This is a paper that I published just last week in GRL. So summer is also important, but less studied, and that's basically because we didn't think that the circulation played a stronger role for summer as it does for winter. But obviously there's some very strong impacts. This is the summer of 1976 again. This was so serious that at the end of it, a Minister for Drought was actually announced. A Drought Act was passed by Parliament. Minister for Drought took office, and then of course it rained constantly for two months after that. We have a more recent example, summer 2007, in the opposite sense. Here, very, very wet, 3.2 billion in property damage. The Environment Agency said that it was a national disaster, essentially. So we'd like to be able to predict ahead of time really dry droughts or really wet summers like this. We've had no systems showing skill before for summer rainfall. However, we've now got an interesting result where this is the prediction of summer Northern European rainfall in this box here over 1960 to present. And so, for example, we can see we have a transition, so the observations are in black again, the model prediction of rainfall is in red. We have this transition from sort of wetter summers in the early 60s to drier summers in the sort of 70s and 80s, including the driest one in both the model and the observed time series being 1976. Wetter summers we have over the sort of late noughties, 2007 to 2012, and then a transition to drier summers we've experienced since then. So this is quite an interesting capability. We have a score of about 0.5 for the correlation, which is a bit less than winter NAO, but represents sort of a step change in our ability to try and predict Northern European summer rainfall. We've used a very large ensemble here of 80 ensemble members, and I don't have time to go into actually the mechanisms here, but you can ask later if you like. But essentially, this nagged ensemble gives us the skill that we need. Here's just some examples of the summer patterns. So that's a pattern from a model from 1976. That's the observed pattern in 1976. So you can see that there's good agreement, not just in the sort of total rainfall, but also in the pattern of spatial anomalies for that rainfall. Less so for the wet summers, but still some correlation. So this paper was out in GOL last week, if anyone's interested. So I've basically very quickly given you an update on our sort of latest sort of skill for our seasonal forecast systems. What I'd like to do now is talk about this assessment of the ongoing risk of extreme events. And for this, we use the large ensembles I've just been talking about. But instead of taking the ensemble mean, we look at every single individual ensemble produced in our large hindcast we have from 1980 to present. And we look at what could happen in that ensemble. So here we're not concerned with predictability, we're just interested in what could happen that just simply has not happened yet because we haven't observed the system for long enough to actually happen in the real world. So put another way, the ensemble diverges. One flap of a seagull's wings may forever change the course of the weather. Small changes now can grow into extreme storms or dead calm in a few months' time. So can we use the computer models to investigate the possibilities? Are they sufficiently good enough yet to do that? So here we're very much using the ensemble members and basically mining them for extreme events. So this was all sort of sparked off a little bit by the January 2013-14 flooding. So this is a picture here, the rainfall anomaly for January 2014. We can see that it basically shows for southeast England for this month of January over 200%. This is saturated, so much more than that over this southeast England, which is a record going back to 1910 when records sort of started. The question is, I suppose, this is a picture of the Thames flooding. Could it have been even worse? And should we have expected it? Anticipated it, I should say. So this is the National Flood Resilience Review, NFRR, which was set up by the UK government chief scientist after the 13-14 and Storm Desmond 2015 flooding. And basically the exam question that was set was, what is the worst case scenario in the current climate? So we did some work on this, which I'll go through in a minute, and we were able to give them some numbers. So to do this, we use the large ensembles we have. So if we look at the recent observations, say for the last 30 years, you've got sort of like 30 cases. We've got about 100 members using various sets of ensembles. Gives us 100 times more data for the model than is available from the observations. So can we make an assessment of these rare unprecedented events, things that have not happened yet but are physically plausible? Now, the advantage of using these seasonal forecasts is that they are started near to the observed state because they are litionized with observations. And so that's quite important. They're not often some sort of model world. They actually are sort of starting near to the observed true state, which minimizes model biases. And the other important point is that they're global ocean atmosphere ones. So they're not constrained by SSTs that are sort of forced into the model. This is a truly sort of coupled global simulation that can run freely for many months or years or decades. So if we think about January rainfall, this is for Southeast England. This is the observed time series we have before 2013-14. And so if you were sort of sitting here 5 years ago and you wanted to know what's going to happen next, you might look back, you might say, okay, we've had quite a few sort of not extreme sort of wet winters in the last sort of 15 years, but there's a couple of, sort of slightly more extreme ones in the past. We should perhaps expect, this sort of level. What actually happened here, of course, was a very unprecedented amount of rainfall in southeast England that broke the records at over 200 millimetres for a whole month in that sort of large region of southeast England. So if you have a look at our model ensembles, this is just one ensemble member here. So this ensemble member doesn't do anything particularly interesting. It sort of shows the correct sort of characteristic of variability, has the right sort of numbers, but doesn't do anything particularly exciting. But if I now add on all the members we have, about half the members we have, then we get this picture here. So we can spot that we have quite a lot of members that exceeded the previous observed maximum before. and even some members that actually exceeded what actually happened in 2013-14. So we can use this sort of information to characterize what the risk actually was of such an event. But first, we need to make sure that the climate model is actually good enough for this task. And so this is a distribution of the model rainfall in red and the observed rainfall in black. Obviously, there's far more data in the red curve than the black curve. And obviously, computer models aren't perfect. This is a 60-kilometer model. They can contain approximations. We need to check to make sure that the model is good enough to do this. I should say that we looked at this in various regions of the UK, and for South East England, the model is good enough to do this task. But for parts of Scotland or Wales, where you have significant orography, then the model significantly underestimated it. But for the flat sort of regions that are sort of South East England, the model seems to do quite a good job. And we assess this by comparing basically lots of resamples of the model, compare it to the observed number, say for the mean or the skewness or standard deviation of kurtosis, different elements of the distribution, to make sure that they all agree that you can't sort of rule out the model based on the observations. So once we've done that task, we can then just simply count up all of these sort of extreme winter months that we have and calculate a risk of such an event happening. So we find that there's a 7% risk of a month wetter than has been previously observed in South East England each year. So each year is a 7% risk, which is a useful number to know. So that's like 1 in 12. So every sort of 12 years, you should sort of expect to see a new extreme month in South East England for rainfall. You can then obviously look not just at what the risk is of an unprecedented event, but also how much does that unprecedented event exceed the previous record. And so there's a 1% chance, a 1 in 100, if you like, that there'll be 15 to 30% more rainfall than has been observed before. And that's obviously a useful number, which went into the NFRR report, and then the Environment Agency used that to then look at some simulations with that sort of hydrological uplift of rainfall. One of the main things, obviously, this gets you is that it's much more constrained using this very large ensemble than you have using the observations alone, which gives you a very large uncertainty if you sort of try to model this using extreme value theorem or something like that. So much more constrained risk estimate. Another thing, of course, we can do with this, because this isn't a statistical model, this actually comes from model physics, we can look, okay, well, what are the weather patterns of these extreme events? Do they look realistic? Are they unexpected in any way? So we have the observed pattern for January 2013-14. Unsurprisingly, we have low pressure just to the north of the UK. This gives us very wet conditions over the UK. Another very wet January was this 1988. And we look at these 4 examples from the model, and we can find one that looks very similar to the observations, sort of this high, low, high, sort of almost a wave train coming out of the tropical Atlantic. But we can also find events, say this one here, which actually are interesting because that would project onto a negative NAO, which is normally associated with cold and dry. But this sort of southward shift of this low pressure being presented exactly where it is bringing particularly moist air from the tropical Atlantic. So that's really interesting to go and sort of see what the patterns are that can drive these unprecedented extreme events. And then we can obviously look for these in the observations. So we published this in Nature Geoscience last year, and we also looked sort of at the other sort of more general case. So if you sort of expanded the statistics from South East England to the whole of the UK, making some assumptions, then essentially there's about a 1 in 3 chance of seeing an extreme new record broken every year in some region or another for a single month. So it's about one in every 3 years we should expect to see some sort of unprecedented extreme flooding event in one of these large regions. So I'll just conclude really. So I've shown that the seasonal forecasts are now providing better forecasts for the upcoming season for the winter North Atlantic Oscillation, which then maps onto lots of climate services such as the energy, transport, river flows. We have just found some exciting Skillful Northern European summer rainfall, which we haven't seen before, and that's still sort of ongoing, trying to understand exactly where it comes from. And then we can use these large ensembles. So it's sort of a novel use of this data. So the same data we've had to do, these large ensembles, to go and counteract the noise, if you like, of the system to find a predictable signal. Instead, we can use these ensembles to explore what is actually possible, but just hasn't happened yet in this risk of unprecedented extremes here. That is where I shall leave it. Thank you.
Do you have any questions for Nick? Let's go to the back first.
Thanks very much. I was just wondering, have you tried calculating up modes of circulation variability in the North Atlantic part of the NEO, so East Atlantic, Scandinavian patterns, jet speed, jet latitude, and so on directly? Because the NEO is quite broad brush, so it's great results, but obviously you must be drawing other things as well.
Yeah, you're right. So we have it. So the East Atlantic pattern and the Scandinavian blocking pattern are two, I mean, they are secondary to the NEO to primary.
They can be important.
But it can certainly be important, absolutely. We don't find any skill for those modes at the moment in the system. So it really is just the large-scale dipole, not the other system. That's in the general sense. However, for individual years, a good example is 2015, for example. So obviously we had that flooding in Cumbria in 2015. That was an extreme El Nino year, a major El Nino event in 2015. And that drove the Wasby wave out from the tropical Atlantic, which basically did hit that East Atlantic pattern and did drive that circulation. So I think it's important to distinguish between sort of state-dependent predictability, so when there's a particular thing happening, and sort of what you can show on average. And that's always difficult, because you can't really sort of, you have to be very careful there. But so I think there is some skill in those modes in particular circumstances, but not in general.
But what about jet speed and latitude?
So we have looked at that too. It's mainly jet speed, not jet latitude, that we're finding the skill for. So the model doesn't really seem to move the jet in the right way, but the speed does seem to be predicted.
Yeah, some of European rainfall results are really interesting. But so any chance of going back to the 1950s? Because the 1950s are in many ways like the last decade. And nearly all the simulations we see of resimulating climate models and seasonal forecasting all start in 1960. And the 1950s are a much more interesting decade.
Yeah, I'd like to go back to that. There's a number of good reasons why we start in 1960, and that's just because of the ocean observations that are available to initialize our models, and the atmospheric initialization as well, because EO interim, for example, starts in sort of 1959, something like that. And if you want to be really strict, some people would think that we shouldn't really go back before 1980, because there we have sort of satellite information, which also sort of helps. And so there are these discontinuities. I mean, there are projects that do try and, like 20th century analysis and things like that, which we could use. But I agree with you that, especially here, it's sort of, you can get this idea that there is sort of a wet sort of period here. I think that's probably coming out of, sort of something like that, essentially.
It's interesting that all our records, 24-hour rainfall set in the 1950s, and so last year.
Yeah.
It's not so bad for you because you're looking at variability, but people who put trend lines in starting in 1960 really annoy me.
Yeah, I wouldn't do that. Doesn't sound like a good idea, though.
I'm curious, we see an increase in extreme events. Are you able to do attribution in relation to trying to understand what's driving it?
I think that's something we might want to look at in the future. We haven't looked at that at the moment. And I'm not sure about that.
You're not showing an increase, though, are you? You're showing that, given the current climate, if you try to estimate the extremes using just the observations, then you will underestimate the distribution.
So
so it's not a climate change.
So that range would go back in terms of if you were to conduct the same experiments in the 30s.
I would guess so.
Yeah, I mean, we have to be slightly careful. I mean, so we use the last 30 years of Pinecast simulations, and we sort of say that that's our current climate, if you see what I mean, and so that risk is representative for the next decade. But obviously, the further you go back, the less representative the current climate will be. So older observations aren't necessarily relevant today. And so this infographic actually rather rudely put them in the bin, which I think was the wrong thing to do. But the idea was that they weren't so relevant any longer, and so it's better. I think the point is that we don't accrue observations very quickly. Every year you get another winter, and that's just going to be too slow. I mean, essentially, as models improve, they're going to be our best estimate, really, of, rather than the observations, ultimately.
But the point about the difference between the 1 in 100 you get from the observations and the 1 in 100 you get from the models will apply whenever you run the model, won't it?
Yeah.
So if you went back 50 years and you ran your model in the same way and compared it with the observations in the same way, you would see the same difference, I think, wouldn't you?
Yes.
Speaking from ignorance, have you ever dabbled in the area of neural networks? Because in certain circumstances they've provided quite good results. So I just wondered.
No. I worked for NELC with 5 years, and I think we did fund a project. I think it might have been Miles Allen's team or something, for neural networks, and tried to do learning from that. What was the bottom of that? Is that changing this?
Yes, I remember something. So certainly in the early days, prediction of the NAO, you could predict the NAO better using either neural networks or regression approaches, provided you chose the right predictors. Better than you could model it, isn't it?
Yes, that's a secret.
Well, that's the advantage.
That's what I'm messing.
And that's the advantage of neural networks, because to some extent, if you give them enough, they will choose the right ones.
But they could also completely overtrain to the historical period.
No, I just wondered whether it would ever be something which.
But the interesting thing is that the models I think are now better.
Yes.
Okay. And
okay,
they are
fine.
now better for ENSO as well, I think.
Yes.
So what those approaches are really good at, I think, is giving us a benchmark and telling us what the important things are sometimes.
Yes.
And then you go to your models and you work on your models until you can beat them.
Yeah, absolutely. It's important to use those sorts of regression analysis to try and work out what's going on, essentially. Here's an example. So in order to work out what's happening with the NAO here, we split this down, look at different drivers. So we have ENSO, we have polar vortex, we have the Atlantic SST tripole, we have sea ice coverage, and you can then do multiple linear regression and try and sort of show where these sources of predictability are coming from, and that's really useful. But using it as a forecast tool, I'm always very nervous about. I've seen so many examples of overfitting to the historical period.